All right, so we continue with surface tension, and most of the questions we picked up are similar to questions which have come in the past in mains, and some ones which are a little more tricky. So let's look at this question here. What is given? S and V are change in surface area and volume when two soap bubbles coalesce. When the, of course, volume will change, the surface area will change. And if sigma is surface tension and if P naught is atmospheric pressure, how are these quantities related? So this question actually, whenever such things are there, we know what will happen when two of them will coalesce. Certain relationships will hold good. We just need to follow the relationship and go for mathematical simplification, and you get our answer. So quite a few questions are something like this. And to make our task simpler, here they have not given whether two bubbles are identical or not. And this relationship, if it is valid for non-identical bubbles, it has to be valid for identical bubbles. So we'll take two bubbles of the same radius. So when the radius of two bubbles of radius are two conditions when they coalesce, number of moles of gas within the bubble remain constant. So here, whenever I have ideal gas equation also will come into picture and will remain constant, and its isothermal process temperature also has to remain constant. So we can use the condition P1 V1 is equal to P2 V2. So that's what we, and let's do that one. Rest all is just making use of the condition. So here, initial values of two bubbles, since we have to calculate change in surface area and change in volume and pressure also involved, let's calculate what the initial area is, what is the final volume is, final area is. Initial case, two soap bubbles. So this is the volume, simply written the value here. Surface area is directly formula. And what would be the pressure? If the radius is R, pressure is P naught, 4 sigma by R. This is pressure, outside pressure plus excess pressure. So that's initial values. And let the final radius be R. Okay. If final radius is R, pressure will be equal to P naught 4 sigma by R. And the change in surface area, change in 4 pi R square is the final surface area minus 8 pi R square. So this 2 will remain here. So I have written S value also, change in surface area for final radius being R. And I've also written V value based on this expression. Final volume also, this is the final volume minus twice this sphere volume. So this becomes S value and this becomes V value. Now what are we going to do? We just apply the condition P1 V1 is equal to P2 V2. So this one is P2, 4 by 3 pi I have cancelled out, P2 into R cube will be equal to P1 V1. So you understand where from this one is coming. So I have, what is the equation I write? P2 V2 will be equal to twice of P1 V1. In that case, I am taking this two volumes of the sphere. The two volumes of the sphere, that's why 2R cube. That's the equation we get here. And once I get this equation, rest all is very simple here. So this arrange, if we rearrange this term here, so I have used this P1 V1 is equal to P2 V2. If we rearrange this term, P naught becomes equal to P naught term. So here P naught term is R cube minus 2R cube, 2 small r cube. Sigma term here, this is sigma term here. And this equation what we get here, if we rearrange the term here. And these terms I need to substitute in terms of S and P. These two terms we have. What is S term we have? In case of volume, R cube minus 2 small r cube can be written as 3V by 4 pi. So I substitute the value in terms of V. And this term here we substitute in terms of S here. R square minus 2R square, S by 4 pi. If I substitute, I get my equation. So this equation, simple, just following through the whole process. Only thing what we do here, because of we use ideal gas equation condition. And once we substitute, we rearrange the terms, we get our answer. Okay. Another important term related to surface tension is angle of contact. And we have shown two kind of figures. If you have a glass and we have a mercury, so the shape of boundary of mercury near to the glass is something like this. And this is how the water shape is when it is kept in a column or it is in contact with a vertical surface here. In a similar way, if we place a drop of mercury, The mercury drop takes this shape, it doesn't wet the surface very well. And whereas if we have water, it will wet the surface here. And this difference in behavior is because of angle of contact. Let's understand what is angle of contact here. See, when we look at this surface here, there are three things involved. Here also three things, three different types of materials are involved, or three different mediums. There's a glass medium, there's a liquid medium, and there's air medium, solid, liquid, gas. And this is the point where all three are present. So there's one point when we take a cross section where, so at one point, all three mediums meet. So when with this common surface here, some are plane, some are curved. Wherever it is curved here, we can draw a tangent here. So these three surfaces, if I draw a line, so this is the boundary between solid air. This is the boundary between liquid and solid. We are concerned with the liquid here. The angle of contact is for the liquid. So I draw two lines. I draw, this is the liquid to solid boundary, and liquid to air boundary is curved. So I draw a tangent here. Draw a tangent here. So at liquid has contact with solid and air, and its surface is curved, we draw a tangent. Angle between two tangents is angle of contact. Angle between liquid solid surface and liquid air surface is equal to angle of contact, which makes very simple sense. So here also, in this case water, this is one boundary, liquid is in contact with glass solid, which is straight line, so no problem. Here it is curved surface, I draw a tangent here. And when I draw tangent, angle between becomes this because my angle of contact here. So what I notice here, angle of contact here is obtuse angle. Angle of contact is acute angle. Similar way, I repeat the process here. Here also I will find, in case of mercury, angle of contact is obtuse angle greater than 90. And in case of water, it is acute angle. Many times, unless it is not given, we take it close to be 0. So this angle between tangents to liquid solid and liquid surface air interface is the angle of contact. Acute angle, and what makes it acute? See, in this case, okay. In case of mercury, the liquid molecule which is at the boundary, it is experiences force due to glass. It also experiences force due to mercury. Liquid molecule with glass is called force of adhesion. The two dissimilar things. Cohesion is similar medium. So liquid particle experiencing force due to surrounding liquid particle is called cohesion, C, and this is A. When C is much greater, angle of contact is greater than theta, 90 degree. When A is much greater, adhesion is greater than cohesion, then angle of contact becomes acute angle. More than that is not necessary. There cannot be many complexity related to this. That's all we need to know. Now, capillary rise. So one of the important phenomena we observe because of surface tension and contact angle is capillary rise. So what does capillary rise mean? If I have a liquid, and within the liquid, if I immerse a tube of a small radius, we'll see why it has to be small radius, and that's why I call capillary. Capillary is a tube of very small radius. We notice here this liquid level inside the capillary is higher than the surrounding liquid. The liquid rises. That's why I call it capillary rise. And when you look at the surface here, the rise is related to phenomena of surface tension. And the surface which forms here, also we have been discussing, and I've drawn the circle many times. This surface also will be part of a spherical shell. Okay, so let's just pay attention here. When the surface forms here, number of things are relevant here. What does capital R indicate here? Capital R indicate radius of the tube. And here theta is the angle of contact here. The surface makes an angle theta with the vertical. So if I draw a perpendicular to the surface here, this angle, if angle theta is from the vertical, this radius vector will make angle theta from the horizontal. R is the radius of spherical shell or surface which gets formed. Surface curvature area is small r. Radius of the tube is capital R. And R will be equal to capital R only when theta is equal to 0. Otherwise, R and capital R are not equal and they are related. How are they related? Is capital R is equal to R cos theta. Or other way of saying, what is the radius of meniscus of which forms? We can also call this meniscus. R is equal to capital R by cos theta. Radius of curved surface which forms here will be equal to radius of the tube divided by cos theta, theta being the angle of contact. If theta is equal to 0, it becomes equal to capital R, both are equal. Okay, so let's do that part. So this is a capillary rise. There we can understand in two different ways. H is the height of capillary, and when we take H height, we take at the bottommost point here. That's H we take here. So there are two ways to calculate capillary rise. One way to understand is take this particular liquid which is in the capillary. What is the liquid which is part of a capillary? If we draw a horizontal surface at the same level as the surrounding liquid, this liquid, this whole thing is the rise of capillary rise here. If I take this as my system, what is system? Liquid in the capillary. This whole thing as a system, if I consider here, it is net force acting on this has to be 0. What are the forces acting? If I take summation of forces in y direction to be 0, there is a pressure acting from the top, atmospheric pressure. And at this level also the contact force will act in from the liquid in form of pressure, which also is atmospheric. So atmospheric pressure on the curved surface, which has projection equal to same as the surface circle of radius capital R. So these pressures will force due to top pressure and bottom pressure both being equal will cancel out. That will not exert any net force. So what are the remaining net force left? Remaining force, net force left is weight of the liquid in the capillary. And there has to be some upward force. What is the upward force? Surface tension force is acting on the capillary. Capillary, this is this liquid surface. It is exerting a pulling force on the wall of the tube here, and wall is exerting a force opposite to that. So that's how the surface tension force will act. It will act an angle theta from the vertical, theta being the angle of contact here. So it will act all around this circular section of the sphere. So it is something like this. If you have it like a something like a perfectly spherical shape, so something like okay, these days you may get some new kind of thing, a fruit which is perfectly spherical in shape. If you make a horizontal cut, you see the skin of the fruit will make a circle here. So it is something surface like this. Boundary is like a circle of radius r. So on that boundary, the surface tension force will act. On what length is the surface tension acting? Surface tension force is acting on the length equal to diameter of circle of radius r, acting angle theta. So what are you going to do here? So if we apply summation of forces on capillary as a system in y direction to be 0, the weight and vertical component of surface tension force acting in the boundary has to be equal. So length, what is surface tension force? 2 pi r into t is the magnitude, and cos theta is the vertical component. So 2 pi r cos theta t is the vertical component of surface tension force. That has to be equal to weight. And when we calculate the weight, we calculate weight of the cylindrical part. We ignore this part to be negligible. So this part is ignored here. That's a small error. If at all you say we don't take care of that error of the small volume, and that has to be equal to yeah. So that's the volume into density into g. Density into volume 4 pi r square into h into g, and I get a value of capillary rise which is equal to 2t cos theta by rho rg. So what we notice here, it depends on cos theta, and if you want to have significant value of h here, t value is normally very small. We have seen earlier also t is very small. Even for water is something like 0.07 Newton per meter. So h to be significant, r has to be small. Small r, very small r, it is inversely proportional to r. It means if I make the radius half, the capillary rise will become double. So small r only gives you significant capillary rise. Very simple formula, and we can. I don't think it. I don't advise it to memorize it. If you understand this part, it's extremely easy to write. Simply, I written vertical component of surface tension force is equal to weight of liquid in the capillary column. And there's another way also to calculate. What is the other way to calculate? Let's do that part also. There's second way to calculate. And what is second way to understand this part also? See, at this point here, the pressure is atmospheric. But as I cross the curved surface here, now I'm finding from interior of the curved surface to outside, the pressure will be not excess pressure, pressure will be lower. The pressure is higher towards the center, outside the pressure is lower. So this pressure just below the meniscus will be atmospheric pressure minus 2T by R. R being the radius of curvature of the meniscus. This curvature has a radius small r. So pressure just below the meniscus will be equal to P naught minus 2T by R. Okay, so that's the pressure right below. And if this is the pressure here, and so this is the pressure at point, let me mark this point as something, pressure at is like this. So I can write if the pressure at this point is P, if I take another point Q here, what is the pressure at this point? Pressure at this point will be equal to atmospheric pressure, but this is also equal to pressure at P plus OGH. What I'm writing here, the pressure at Q, which is equal to atmospheric pressure, which is at same level as the liquid outside. So P naught is equal to P naught minus, okay, I have put I have written R in terms of R by cos theta. So this small r I have replaced in terms of radius of the capillary tube. So small r is equal to, I have done it earlier also, small r is equal to R by cos theta. I put this value here, it becomes this plus rho gh is equal to atmospheric pressure. From here also, I get the expression of capillary rise, which is same as before. So there are two ways. One is in terms of using a concept of excess pressure. This side is excess pressure, this side excess pressure is here. Atmospheric pressure is greater compared to the pressure on the other side of meniscus by d by r. So we can arrive at capillary rise in two ways. Okay, and in this case, what is noticed, this theta is valid for all cases. If contact angle is 90 degree, what will happen? If contact angle is 90 degree, which means if, then there's no capillary rise and capillary fall. But if angle of contact is greater than theta, this H value turns negative. It will actually, in case of mercury, the liquid level falls. So there's capillary depression rather than capillary rise here. So this formula is valid for all values of theta. It could be even greater than 90. When theta is greater than 90, it will get H negative, which is capillary fall. And we can also, there are other ways also we can get capillary rise. Another way you can get capillary rise is if in a liquid, if we insert parallel glass plates, so it could be any other material. Parallel glass plate, again keep the distance between parallel glass plates small. So these are two vertical parallel glass plates with a small separation. And it's a long plate, and this something, it will take an odd shape. It near the boundary, it will not be rise like this. It will have something shaped like this. It will take a curved shape, something like this. We are not concerned about the end part here. End part shape of liquid will be complex. If we have a long parallel plate, only in the central part I'll find the liquid will rise to a particular height. I'm looking only in which region? We are looking only in the central region of parallel plates. This is like a 3D view. This is like a side view. Side view in rich region, central region. So there also I'll feel the capillary will rise. Let's try and understand how do we calculate capillary rise in this case here. So two large plates placed vertically parallel to each other inside a tank of water with separation between them is B. We'll just find in terms of variable, we can always substitute and find an answer. And the rise of water in the space between the plates. Which plate? Not in the end region. End region will take a complex shape. I don't want to draw that shape also. Surface tension is given. So here also, what we'll do here, to consider unit length of the plate. So from what is the length I'm considering here in the central region, this length I can consider length L, or you can take a unit length also. Let's take a unit length. So the length is equal to 1 unit. If I take length is equal to 1 unit, I am looking at dimension perpendicular to this figure is 1 unit, and in the central region to avoid end effect. The vertical component of surface tension force also has to be equal to weight of the liquid in the capillary. Again, I write the similar way. Only thing what will happen, earlier the capillary was forming a cylinder. Now it will not form a cylinder. Volume of capillary will be different. Let's write that equation. So vertical component 2T, over what length the tension will act. Each surface the tension will act over a length equal to whatever length, unit length we have taken. So each side the force will act over T into 1 on this side, T into 1 on the other side, and then take the cos theta component. So 2T cos theta is the vertical component acting on this capillary rise of unit length, and that has to be equal to weight of capillary. What is the weight? Weight is density into volume. What is volume? Cross section into the depth here. Cross section is B into H, and depth is 1 unit into G, and this expression we get here. So that's a capillary rise in case of parallel tubes, parallel plates. And again, I think it's so simple. I don't suggest that anybody need to memorize this one. Okay, so that is all about surface tension. Then we move on to one more property of liquid called viscosity. Viscosity is something similar to friction force. Just imagine this is something, so you can think of liquid composed of infinite number of parallel layers. So we have a liquid here, a liquid of certain thickness, and the whole liquid we are thinking of several small parallel layers is just like your book. If you take a book or notebook, there's several sheets in the book, and each sheet, suppose the sheets are really smooth, and you can see some of the papers which are smooth, like papers what you use for printing photograph. If several sheets are kept on top of each other, and if there is slight friction, you push the top sheet, what will happen? All of the sheet also will start moving. So that's what happens in case of viscosity. We'll imagine the liquid to be composed of infinite number of parallel layers. If the top layer is given a velocity, so top layer, how do you give a velocity? See, suppose it's a prototype. If I keep a plate here on the liquid level, if I move the plate here, liquid layer sticking to the plate layer also will move with the same velocity. So when I keep a plate, kind of metal plate or any plastic plate or any material, if I keep a plate horizontally on top of a liquid surface, which can be like a boat, also flat boat, and if that is moved with a constant velocity v, what we'll find, the bottommost layer which is sticking to the lower surface, the layer which is sticking to it will remain, it has same velocity, it will remain at rest, and the top layer which is sticking to the top plate will have velocity of the plate, and in between the velocity may vary. And since this velocity is v and this is 0, and most cases we assume the velocity will vary in a linear fashion. Will vary in a linear fashion, and this is called linear velocity gradient. So if this is in the microscopically, if I look at, if I have 7 sheets of thin films, thin paper film which you use for photography now. So if I keep all the sheets here, if there is small friction between them, if I push the top sheet with some velocity, I'll find all other sheets will move. Only the sheet which is bottom sticking to the surface will not move. Something like this may happen. Okay. So this is a shape. So any liquid, if I just focus on the liquid here, which was in a rectangular cross section earlier, if I start moving the top velocity, little time later, I see it like this. After time delta t, if a top plate is moved the velocity v, this liquid also, all liquid particles which are in contact with the plate would have had a displacement v into delta t. Other particles will have lesser displacement, different layers will have different velocity and different displacement. So velocity also is something like this, linear gradient. So whenever there's a relative velocity, so basically if we imagine a separate sheet here, since velocities are different here, and this slipping taking place. So relative velocity, relative motion, velocity gradient gives rise to shear force. The force which acts along the surface is called shear force, which is something similar to friction in case of solid. So this is shear stress. So basically what will happen, the different force, since there is a relative motion, if liquid is not ideal, if it is viscous fluid, friction force will act, and the force which is acting along the surface per unit area, force per unit area becomes like a stress. We'll come to the stress part also tomorrow. The force per unit area which is acting along the surface is called shear stress, similar to friction, and this shear stress which will develop between different layers will depend on the medium as well as velocity gradient. So what is the shear force between? So what is the force I need to apply to move the plate here? I can calculate that force here. That force will be equal to eta times, eta being viscosity. It will be proportional to area, and it also proportional to velocity gradient, dv by dy. And if velocity gradient is linear, I could have written as eta a delta v by delta y. What is which direction is the changing? Which is y direction? Y direction is perpendicular to velocity. So if velocity gradient is constant, I can write f is equal to eta into a, and e is called coefficient of viscosity, which is property of the material. And if you want to compare viscosity, you can imagine. So if I have two surfaces, one is water, other is honey. Both are the same thickness, in which case I will have to exert more force to keep the plate moving the constant velocity. In case of honey, the plate which is kept on honey will take more force. The reason it will take more force to move at a constant velocity. So suppose there are two rivers here, two shallow rivers. One case boat is flowing on a river which is filled with water. Other case river with a small very small depth here, a shallow river, or maybe channel, which is filled with the honey, same depth. If we have to move the boat in both the cases, the power required or force required to move identical boat in honey will be much larger because coefficient of viscosity in honey is higher. You can imagine a different type of liquid what we observe here. We get an intuitive sense of how the relative value of viscosities are. So that's a viscosity. It's like a frictional kind of property between the different layers of liquid. And that's what the friction force will act on the area. If force by area, if we take the stress, the shear stress is eta times delta V by delta Y. That's the shear stress. And unit for viscosity, I think from here we can rearrange the term, we can easily find out. Unit for viscosity, 1 Pascal second. Pascal second is the unit, stress into second. And that is equal to 10 poise. So 1 poise is equal to 0.1 Pascal second. And poise is more commonly used unit. This is not an SI unit. So whenever poise is given, we multiply by 0.1 to convert into SI unit. So let's look at some simple application of the same. And again, this is something some of you may think we are back to laws of motion. Yes, it looks like laws of motion question. So there's a block of mass M here, and it has some cross-section area A. And it is placed on thin layer of oil having thickness T. What you see here, there's a thin film here. It's a thickness is T, viscosity eta is given, and this placed like this. And you can also call this, perhaps this may have lower friction then, and it can have lubricating layer. So you see, wherever you use lubrication, you will have a thin layer of oil kind of thing, which will have low viscosity if you want to use for lubrication. So when you have something like this, and it is to an ideal pulley, it is attached to a mass M here. The question is find the mass M which need to be connected to ideal pulley so that the block may move with the constant velocity V. It is moving in the constant velocity V. So what has to be value of M for it to move with the constant velocity? That's what you need to calculate here. Okay. So is this question related to viscosity? Yes, there's a liquid film here. And as we move here, as we magnify, the bottommost layer of the film will be at rest, and topmost layer of the film will have same velocity V. So what will be the velocity gradient, assuming the velocity gradient to be linear here? Velocity gradient of the thin film here equal to V divided by its thickness. That's what we have done. Delta V by delta Y, and delta Y will be equal to thickness here. So we get velocity gradient is equal to V by T. That's the only thing. So what force need to be exerted in the liquid? Liquid will exert opposite force on the block here. The force exerted by the liquid when the block is moving the velocity V will be equal to eta times A into dV by dy. Let's put those values. So this what is the force? So this viscous force exerted by the liquid on the block has to be equal to tension in the string for it to move with the constant velocity. So this T has to be equal to viscous force, and since velocity is constant, this T is nothing but equal to mg. Mg has to be equal to viscous force. So mg is equal to eta into area of the block, and this is velocity gradient V by T. T is the thickness, not time here. So that's expression. So that's value of m required here. Okay. Other case we have taken, sometimes velocity gradient may not be linear. So here what is given, a thin plate of areas pulled on a thin film of castor oil. Coefficient of viscosity is given twice. If I have to convert into SI unit, I divide by 10 to convert into SI unit. Then I can substitute everything in SI unit. Thickness of the film is given as 0.2 centimeter. Velocity of the layer varies. Even in the small thickness also, velocity of layer will vary. So what is velocity as a function of y? This is the velocity, how it varies with y. So if I have to understand how does the velocity vary here? So if what does this mean here? See, this is something, this x direction, this is the direction in which the motion is taking place, and y direction, vertical direction, that's where the thickness of film is, And this says if I take this is minus 0.2 centimeter. So here the velocity is 0, and it varies here. It varies the square of y. So velocity shape, it will look something like this. Velocity is varying like this at different levels. Okay. So where the plate is thin plate is kept here. So thin plate here, this thin plate is in contact with our next layer of liquid here. And between this thin plate and the liquid, shear force will act. Which is the liquid layer? This is the liquid layer which is act. And what is the force? Viscous force will act at this level. This viscous force acting at this level will depend on what is the velocity gradient. It will depend on what is the velocity gradient at y is equal to 0.2. That's what we need to do here. Okay, so let's do that part here. So force acting on the plate is equal to, this is something very eta into A into dV by dy. Since this is not linear, I'll find dV by dy. dV by dy comes equal to, is if it is given SI unit, y comes equal to, okay, the plate, and we need to calculate dV by dy at which point? Y is equal to 0.002 meter. So I need to find dV by dy at y is equal to 0.002. dV by dy, this value, I get 2000 into y value. So this is the velocity gradient. This will be the slope of velocity and y curve here at y is equal to 0.02. Once you have this value, rest is simple substitution. I get the value of eta into area convert into SI unit, and into velocity gradient, which is already in SI unit. That's how we calculate. One more variation of there, yeah. So this is something wherever something slipping is happening. So this is case a long cylinder, and in case of engineering application, these kind of things are also common. So let's try and understand what the question is given here. The long cylinder of radius r. So this is the small r. This is the cylinder. Okay. And this cylinder is placed inside another. This is cylinder. And there's a small gap between is placed inside a hollow cylinder. Inner radius is r dash, and of course r dash is slightly greater than r. So one cylinder is placed inside a hollow cylinder, and this is the length dimension. We see from the cross section, this is the dimension, and space between two is filled with the liquid viscosity. What is the force required to be exerted per unit length of the cylinder to move with the uniform velocity v? So this inner cylinder, outer cylinder is at rest, and inner cylinder is moved with velocity v. So if I look from here in the cross section, so the liquid which is, if I took the top, the liquid here which is in contact with the top surface at rest, and liquid which is in contact with the inner cylinder, it is moving the velocity v, and this we assume a linear velocity gradient. This is how the velocity of liquid layer will be. Liquid layer which is in contact with the inner cylinder had velocity v, and which is on outer cylinder has zero velocity. So what is the velocity gradient here? Perpendicular to direction of motion. Velocity gradient is for what distance is the velocity changing by 0 to v. This distance is nothing but r dash by r dash minus r. Or a distance, so when you look at v by delta y, what is delta y here? So area is of course over what area this force is acting. The surface area which is in motion. Surface motion is not a flat surface, it is curved surface, but I can take the total area. Total area will be perimeter into the length. Length is 1 meter. So total area which is in contact with the liquid which is in motion is 2 pi r. And what is delta y here? R dash minus r, and velocity v. Rest all we substitute, we easily get our answer. Hence force required is eta into surface area per unit length into velocity gradient. Velocity gradient will be v into r dash minus r. This is one way when it is moved along the length direction. Yes.
Sir, can you explain how we got the area of cross section here, sir?
You tell me what is the area which is in contact with the liquid? Unit length. Tell me what is the area which is in contact with the liquid? If I take unit length of the cylinder, what is the area which is in contact with the liquid? If I take a side view, how would the side view look like? Side view look like this. Okay, let me draw the side view also something. So this is the inner cylinder. This has a radius r, and there's a hollow cylinder which is slightly higher radius. This is cylinder. Just give me a second. There's something at the door. I'll just come back in a moment. Okay. See, this is how it will look from the side, and where the liquid is filled up in between this area. Okay. And if you look from the side, all this liquid particle here, this is the liquid is in contact over this perimeter of this circle. So what is the area of contact which is in motion? This entire perimeter of the circle, which is perimeter of the inner cylinder, which is in a state of motion. It has a velocity equal to v here, and this has zero velocity. So if I look at any particle, liquid particle here, which will remain at rest, this liquid particle will move towards me with velocity v. Anything in between will have velocity v by 2. So it is similar to basically what has happened here. Rather than whole thing being flat, it has been folded in form of a circle. So that's how the force will come. So this is one way, but you want to understand, is this understood now?
Yes, so we take the area which is in contact and flowing with the same velocity, right?
Yes, of course. The area in contact which is in motion. So in all particles here are able to velocity v here, and this is zero velocity, and velocity will vary in the linear fashion here. So this is from 0 to v, like this. So this whole thing, you can flatten it out. If you flatten it out, it becomes like a flat plate. So if I, something like this, that's what it is. Okay, then. So I think this is clear.
Yes.
Okay, and we can have small variation of the question. Let's try and see that we understand that part as well. See, other thing what you can do, we can also rotate. So what happens when inner one is rotated? Earlier it was moved along the axis here. Now it is rotated above the axis. When it is rotated with the angular velocity omega, a unit length, what is the torque which will act? So now to make this cylinder rotate, I need to apply a torque. You know, understand how do I apply torque? If there's a handle here, if there's some handle here, I can apply a torque here. What is the torque required to rotate this cylinder of unit length with angular velocity omega? In this case, how is the liquid particles moving? All the liquid particles rotating like this. This particle is having velocity r omega. This is having velocity r omega. This is having velocity r omega. And whatever velocity of this point has zero velocity. So in this case, if we have to calculate what is the torque required, just understand here. Let's see that part. So in this case, if I take a small piece, let's take a piece. This is a small part of the cylinder. Now this will be like a plane surface. Okay, this area is d theta, and its perpendicular direction is 1 unit here. So what is this area equal to? This area will be equal to. This becomes like a flat plate, and this is moving on the surface, and in between the velocity is varying from 0 to r omega. V is equal to r omega. How much force will act? D theta. So if I take what is the area here, area will be equal to r d theta. Hence, force will be equal to eta times area r d theta into velocity gradient. Velocity gradient will be equal to r omega divided by what distance? R dash minus r. This is force which will act on a small piece. And if this is a force acting, what will be the torque it will create? Torque will be equal to df into r. And if I add up what the entire area, it becomes, if I add it up, d theta, it becomes 2 pi r. I can arrive at the total torque also. And torque will be equal to F into R, as all parts of the force will be acting in the same distance at R. Or I can write torque is equal to, yes, this is the value of torque which will come. So you can just see that this part is also understood. Okay, so I'll stop here.